Good day, everyone. Today we shall be considering Kirchhoff Law. Under this, we shall be considering the Kirchhoff current law, Kirchhoff voltage law, examples involving Kirchhoff law, and practice questions with answers.
Kirchhoff current law. It says that the total sum of current leaving a node or junction is equal to the total sum of current entering the node. The Kirchhoff current law can be illustrated as shown diagrammatically. So we're trying to illustrate the Kirchhoff current law using this now. This is a node where this circuit element meets. That's the node. So the sum of current entering this node is equal to the sum of current leaving the node. I simply sum it up like this, that entering is equal to leaving. So sum of entering equals the sum of current leaving. So we have to come here and look for the current entering. As you look at this branch now, the current is leaving. As you look at this branch now, the current is entering. So the entering is the I2, I3 is leaving, the other entering is I4. So the only entering here is I2 and I4. I2 plus I4 is equal to the one leaving. The leaving is the I1, I3, and then I5. I1 plus I3 plus I5. So this is the Kirchhoff current law. The total sum of current entering a node is equal to the total sum of current leaving the node. Kirchhoff voltage law, the KVL. It says that the algebraic sum of voltages in any closed loop is equal to 0. The Kirchhoff voltage law can be illustrated using the circuit below. And so we have this circuit now, and I want to illustrate the Kirchhoff voltage law. Now, the first thing I will do here is to say applying KVL to mesh A, B, E, F, A. So I'm applying the KVL to the first mesh. This mesh can also be called a loop. So I could have said applying KVL to loop A, B, E, F, A. And that's still correct. Now, you see, this thing simply tells me that I am moving from A to B, B to E, E to F, F to A. Although it does not mean that you necessarily must start from A, but you must keep going like this. I could start from F, but maintain the same direction. From F to A to B. If you start from E to F, F to A, don't go from A to F. You are not going anti-clockwise, which is not the direction this thing gives to me. This direction actually is called the loop direction. The direction you are taking in reading your elements means that you must go from this to the next one, on and on. You shouldn't go in the reverse order. That is, we say, maybe anti-clockwise. So that's that about that. Now, let's start now. Let's actually start from here. Sometimes I'm going from F to A. Now, when you go from F to A, you will only meet one circuit element, which is the cell. For this cell, how do you read the voltages? Because we're trying to sum up all the voltages in this first mesh and equate it to 0. So, how do you read this voltage of this E1? Well, it is given as E1. The question is it going to be positive or negative? Well, quite an easy one. You know, I'm going from F to A. Like I said, you necessarily must start from A to B. No, you can start from F. You can even start from E. So let's take from F first of all to A. When you take from F to A, you meet this cell having an EMF of E1. Now, it's going to be positive. Why? Because a cell has the short terminal and the long terminal. The long terminal indicates the positive, while the short one indicates the negative. So, as you move from F to A, you understand that you will meet the short one first before the long one. Because I'm meeting the positive one, that's the longer one lastly, it's going to be positive. So it's like plus E1. So if I meet the short one lastly, the last one I met was the short one, then it's going to be negative. But obviously, going from F to A, you meet the longer one, which is the positive first, lastly, sorry. And that makes it positive. Then, nothing else to read there apart from this cell. So I'm going from F to A, and I've read the only thing I can see there. Now I'm going from A to B. The only thing I can see is this resistor. To get the voltage in a resistor, you apply Ohm's law. And Ohm's law says the voltage is I times R. what I is flowing here? That's the I1. This I1 flows across this part, and this part. So this is the entire place this I1 flows. So any resistor meeting this part, we have I1 flowing through, this I1 flowing through it. Now, to get the voltage here, it's going to be I1, R1, applying the voltage, the Ohm's law now. The next question is that, is it going to be positive? Now remember, I'm going from A to B because I finished from F to A. Read the only thing I can see there. Now I'm going from A to B. I'm reading the next thing I can see. I've read it as I1, R1. But is it going to be positive or negative? Well, it's going to be negative. Why? Because I'm going from A to B. That's my loop direction. And if you look at this current is also going in this manner, in this direction. So because I'm going from A to B and current is going the same direction with me, then it's going to be a voltage drop, negative, minus. Because the current direction and my loop direction is the same. Now, the next one is that we go from B now to E. From B to E, we see two things there. We are seeing the R2 and we are seeing the E2. Now, what are we going to do? Let's read this one first of all. The current flow in this branch here, from this B to E, is I2. So any resistor I meet here, we have I2 flowing through it. So for this resistor 2 now, the voltage across it will be I2 and then R2. Now, I'm going from B to E. Now, let's watch the current. How is the current going? The current is going down in this manner. So, the current is going the same direction as I am going. I'm going from B to E, and current is also going downward. Because of that, it will also be a negative voltage drop. So, a voltage drop, that's negative voltage. The next one is that this E2. This E2 has nothing to do with the current. It's the terminal you will see lastly. I'm going to see the short one last and go from B to E. Because of that, it's going to be a negative E2 minus E2. So I'm done reading everything in this middle part. The next one is from E to F. From E to F, there's nothing there to read. So because of that, I will say I am done reading from F to A to B, B to E, and back to F. So because of that, everything will be equal to 0. This is the KVL. Now, sum of the voltage around a closed loop or a closed mesh is equal to 0. Now, again, I will apply the same KVL again. Applying KVL to mesh B, C, D, E, B. Well, that happens to be the second loop. That means this other part now. And how is it going to be? Well, let's start from this part now. From B to E, I am meeting this R3. Understand that this I3, this current here, flows across this entire branch here, here, and here. So every resistor I meet here, we have this I3 flowing through it. So let's proceed now. If I move from B to C now, I am going to meet this resistor here. And the voltage across it, we can get it using Ohm's law, IR. So it will be going to be I3, R3. But mind you now, the current is also going in this direction. I'm going from B to C, I can't go in this direction. It's going to be a negative voltage or a voltage drop. Now the next one, I'm going to go from C to D. And what I will see from here is the E3, this cell E3. So since I will see the short one lastly, it will be minus E3. Now the next one is that I'm going from D to E. It will be I3, R4. Because I3, I told you, is what flows across this entire branch. So I3, R4. Now, is it going to be negative or positive? Well, quite an easy one. It should be negative. Why? This current goes like this and goes like this, and we still go like this. So I'm going from D to E. Why this current will also go in the same manner? So it's going to be negative. Then it's now going to remain from E to B. From E to B, I will meet this cell E2. And what is it going to be? Plus E2. Because you can see that we see the longer one lastly. And then again, I will see this resistor. The voltage across that resistor will be I2, R2. But is it going to be negative or positive? Well, positive this time around. Why? Because I'm going from E to B upward, while the current in this part is going downward. So that's about that. So it's plus positive. I put plus here. Everything now equal to 0. So that's about that. Please take note that as we move from B to C, C to D, E to B, that I3 does not flow in this middle part. It only flows in this part. And I1 does not flow in this middle part. It only flows in this other branch. I2 is what flows in this middle part. Please do not confuse that. So we have 3 different currents flowing in each branch. And we have 3 branches here. 1, 2, and then 3. Where there is a third mesh. Or not actually mesh, a loop. You can't call it a mesh this time around. Take note that A, B, E, F, A is a branch and a loop. B, C, D, E, B is a branch and a loop. But you see now, applying KVL to loop A, C, I'm talking about from here to here to here to here, as though there is no middle part. So it's as if we remove everything in the middle part, just this part alone, this entire part. We don't call this big one a mesh. It can only be a loop, because this big one is what contains the ABEFA and BCDEB inside it. So a loop can contain smaller meshes inside, the smaller loops inside it, but a mesh cannot contain. That's why ABEFA is qualified to be called a mesh, but cannot, and a loop, because it does not contain anything inside it. That's why it's qualified to be called a mesh. BCDEB is qualified to be called a mesh because it does not contain smaller ones inside. But this ACDFA is not qualified to be called a mesh because it contains smaller ones inside. That's, by the way, we've explained that when we explain the terms used in circuit theorem. Now let's take this one now. For this one now, let's start from A to B. It will be I1 R1 but negative, and then from B to C now, it will be minus I3 R3, I1 R1, I3 R3. When I get here, it will be minus E3. Here it will be minus I3 R4, and then nothing here, and then from here E1, it will be positive E1 equal to 0. So that's for this loop ACDFA. So this happens to be our third equation. This is equation 2, and then this is equation 3. Well, for this third one, whenever I'm solving Kirchhoff Law, I don't often use it because the 2 equation is enough to give us our answer, especially when we apply Kirchhoff current law firstly before applying the KVL. So that's that about that. We're going to be taking an example now. Example 1. Use Kirchhoff law to determine the current flowing in each branch of the circuit. And so this is the question now. Like I said, there are 3 branches here. 1, 2, and 3. So unfortunately, the current directions weren't given to us. The branch current weren't given to us here. If you have a question like this where the branch current is not given, you have to assign branch current. But I think in most questions, the branch current will be given to us. So this is the branch current I assign. You can assign anywhere actually. There's no penalty for that. Another person can choose his own I2 to begin like this, or even call this on I3, or can call this on I2. Whichever way, it is still correct because it was not assigned to you. It is when it is already assigned, you don't need to touch it. If you touch it, you'll be defaulting and you'll be wrong actually. That's that about that. Now, let's analyze now. So the first thing I will do is to apply both Kirchhoff current law and Kirchhoff voltage law here. Apply KCL to node B. I've often said that. Well, okay, let me forget about that. Let me not, because it's not relevant here. Maybe in the next question it should be relevant and I will say it. So here now, understand that I'm applying KCL. Now you're not going to apply KCL to branch to node where only 2 circuit elements meet. It's where the 3 circuit elements meet. That's why you're going to apply your KCL. So here now, 3 or 4 or more than 2. So this is where we're applying Kirchhoff current. Like I could apply it here too. There's no problem. But let's apply at node B. You remember, sum of current entering a node equals sum of current leaving the node. So as I look at this thing now, there are 3 branches attached to it. 1, 2, and then 3. In each of those branches, how are the currents? Are they entering this node or leaving the node? So let's watch now. For this branch here, the current in this branch, I1 is entering this node. Current in this other branch here is entering this node. And the current in this branch is leaving the node. So it will be entering I1 plus I2 is equal to I3. I can call this my equation 1. Then I'm going to apply KVL to mesh B, C, D, E, sorry, not BC, A, B, E, F, A. Going from A to B, on and on. So from A to B, there's nothing there. So let's go from B to E. From B to E, we have the 4 ohm resistor, which is the R2. So it will be 4 I3, because the current flowing is I3. So 4 I3. I1, IR, Ohm's law. So for the resistor and the current. Now it's going to be negative. Why? Because I'm going from B to E and current is also going downward. Now let's go again from E to F. There's nothing to read there. Now let's go from F back to A. From F to A, the current flowing here is I1. So it will be 2 I1. But understand now, how is this current flowing in this middle part? In this end here, it's flowing upward. See the direction of the current. It must have gone like this, and like this. So this I1 must have flowed from E to F, F to A, and A to B. So the current is actually going upward. So that's why this is going to be negative, minus 2 I1. Then for this battery here, is going to be plus 4. Why? I'm going to see the positive longer arm lastly. That's why it's plus 4. So is equal to 0. This should have been my equation 2. But we go ahead. Remember, there's I3 here. But I3 in equation 1 says it is I1 plus I2. So from equation 1, we have it that I3 is equal to I1 plus I2. So I'm going to substitute. This is my equation 2. So we substitute into equation 2 now. Doing that, I will have minus 4 into brackets. Instead of I3, I'm going to have I1 plus I2. Then minus 2I1 plus 4. So this will give me minus 4I1 minus 4I2 minus 2I2, 2I1 plus 4 equals 0, please. So this will be minus 6I1 minus 4I2 plus 4 equals 0. So this is going to be 4 being equal to 6I1 plus 4I2. This is equation 1. This is equation 3, sorry. So again, apply KVL to mesh BCDEB. BCDEB. So from here, B to C, no circuit element. But from C to B to D, we have 2. We have the E2 and this resistor here. So for this E2, it's 2 volts minus 2, because I've seen the short arm lastly. Then going downward again, you meet this resistor here. It's going to be 1 times I2. So that's 1 I2, which is I2 actually. Now, mind you, now it's going to be positive. Why? Because the current I2 is actually flowing like this, in this manner. And then I'm going from C to D, and current is going like this. So it's going to be positive in opposite, where the current and the loop direction is opposite. So it's going to be positive. The voltage gain. From D to E, there's nothing there. And lastly, from E to B. From E to B, we meet again plus 4I3. Plus, because I'm going from E to B and current is going downward, opposite, is equal to 0. So this happens to be my equation 4. But again now, since I3 is equal to I1 plus I2, substitute that now. That will be minus 2 plus I2. 1 I2 is I2. Because 1 times anything will give itself. Then plus 4 into I1 plus I2. That's substituting this I3 for I1 plus I2 is equal to 0. So at the end of the day, we have minus 2 plus I2 plus 4I1 plus 4I2 equals 0. And then this will give us 4I1, yeah. Then this plus 5I2 is equal to 2. This happens to be our equation 4. So I will simultaneously solve now. Simultaneously solving equation 3 and 4. So equation 3 now is 6I1 plus 4I2 is equal to 4. And then 4I1 plus 5I2 is equal to 2. This is equation 3 and this is equation 4. So we can simultaneously solve this. I don't want to show the simultaneous equation because this class is not a class to teach simultaneous equation. But when we solve simultaneously, we get I1 to be equal to 6 over 7 ampere, and you get I2 to be equal to minus 2 over 7 ampere. And then you will get your I3. Remember, I3 is I1 plus I2. And that will be 6 over 7 plus minus 2 over 7. This will give us 6 plus minus 2, which is 6 minus 2 over 7. And that's 4 over 7 ampere for our I3. So that's that about this question. What would have happened if somebody has chosen this other direction for I2 and then take this direction for the question? What would have happened? Well, quite easy. The person would have gotten I2 to be 2/7, not minus 2/7. But the same value, just a difference in sign. If someone had taken the other direction for I1, we would have gotten minus 6/7. That's just what happens. But your value will be the same thing, just the sign that would differ. That's the example 2. Find the value of the branch current in the circuit below. And so to solve this now, we begin by saying, applying, so I'm solving now. Solution. Applying KCL to node B. So entering, sum of entering equal to sum of leaving. And so the entering here is I1 and I2. So I1 plus I2 is equal to the leaving here is I3. Again now, apply KVL to mesh ABEFA. That's the first mesh. This will be plus 5I3 because I'm going from here to here and current is going the opposite direction. Then again, plus 2I3. Then on getting here, it will be plus 3I2. And that's because from here to here, I'm going from B to E and current is going the opposite direction. So a positive voltage or voltage gain. Then this will be minus 10 because I'm going to see the shorter terminal lastly. Then no voltage to get. I've read this, I've read this, I've read this, and I've read this. Equal to 0. So from here we can say 7I3 plus 3I2 is equal to 10. Then I'm going to say, remember that I3 is I1 plus I2. So recall that I3 is I1 plus I2. So this 7I3 becomes 7 into I1 plus I2. Then plus 3I2 is equal to 10. We can expand this. This will become 7I1 plus 7I2 plus 3I2 equals 10. And this will give us 7I1 plus 10I2 equals 10. This becomes my equation 1. Again, apply KVL to mesh BCDEB. Let's go with that now. Starting from here, this will be 4I1 positive. And that's because I'm moving from B to C, where current is going in the opposite direction. So a voltage gain. Then this will be minus E2, which is minus 12 volts. Nothing is here. And then this will be plus 10. And then minus 3I2. Plus 10 because I will see the longer terminal lastly. That's positive. And then here, I'm going upward. I'm going to go in the same direction. This is equal to 10. So we have 4I1. Yeah. This is 12 volts. That's 12, please. Then minus 3I2. We're going to have minus 12 plus 10. That is minus 2 equals 0. So this will be 4I1 minus 3I2 equals 2. Equation 2. So simultaneously solving equation 1 and 2. That is 7I1 plus 10I2 equals 10, 1. And then 4I1 minus 3I2 equals 2. Okay? So let me evaluate this now. Okay, so we are going to have I1 to be 0.82 ampere and then I2 to be 0.426 ampere. But recall that I3 is I1 plus I2. So that will be 0.82 plus 0.426. So 0.82 plus 0.426. That will give us equal to 1.246 ampere. So that's that for this question.